Hello, let's continue with the next topic called swapping. So in fact, this concept we already mentioned a little bit before. So the basic idea is that if some code or program is not needed, we can temporarily load it out, and then we load some data or code which will be shortly used in the future. So this will utilize the memory in a good manner. Okay, so called swapping. So a process can be swapped temporarily out. That means one is swapped out of the memory to a backend store. So why we don't save it into disk? Because this is based on the statistics. Mainly, if a program is recently used, it is more possible for that program will be used again. So rather than save it into the disk, we put this program into a backend store. So this backend store is in fact is quicker than the disk. So that means later if we need it, we can load it back into the memory again. Okay, this is the idea. So temporarily load out and then brought back into memory for continued execution. So that means temporarily load out, and then if we want to run this one, we load it again into the memory to continue the running. Of course, we don't have to do swapping. The main reason is that we don't have enough memory to run processes. So we have to load something out. Then we can load a new data to run data and code to run that process. So this is the main reason. Okay. So this one we have give you a feeling. So the program, the system can run programs which is larger than the memory space. For example, you may process 100 gigabytes data, but your memory is only 4 gigabytes or 32 gigabytes or 64 or whatever, but it's still less than that 1000 megabytes. 1000 gigabytes means 1 T, right? 1 terabytes. But we still can run run the program on that big amount of data. Why? Just because we don't load them all into the memory at one time, at once. We just load the data which will be processed shortly, and then once processed, we may load it out. We may load it again, but maybe not. Okay? So that means we can load the data in and then load it out. This will just let the computer run on your data, which is much larger than the memory space. Okay, this is the idea. And then here we have a backend store rather than just load it into a disk. That is a fast disk. Okay, and also large enough. So the reason is that we want to save temporary data which has been used recently. So we may want to find it again. So rather than just load from the disk, that will be slower. Okay? So it is fast disk. So of course this is just some hardware design. You will reserve some space from the disk, which can be quickly accessed by the memory. Okay, this is the idea. And also the size of this reserved space is large enough to save the temporary loaded out data. Okay, so this is the idea. And also we must provide direct access to these memory images. Direct access, that means you can just load them quickly. Okay, you can find the space, the address and the space, the location quickly. So for this one, it's like a roll out and roll in swapping variant used for priority based scaling algorithms. So that means if we are dealing with scheduling based on priority, if we are is a high priority algorithm coming here, we may need to temporarily put a running task into a lower priority. That means a waiting state. So because this process is not running, and then we want to run a high priority task or process or whatever thread. So this one maybe need to have some additional space to keep running, to continue to run. So that's the reason we may have to load it out, roll in, roll out. Can roll out the lower priority process occupied resources, mainly for the memory. Of course, just CPU will be preempted by the high priority process. So this one is the lower priority process is swept out, so higher priority process can be loaded and executed. So maybe even no space to load that process, not alone the data cut. Okay, so mainly during this swapping, we have load in, load out, so it takes time, cut. And also what time will be used depending on how much size you will load in and load out, cut. So total transfer time is directly proportional to the amount of memory swapped. Of course, the unit will swapped. For example, you want to swap 4 megabytes, and then you will load approximately 4 megabytes. You don't need to load out maybe 8 megabytes, but load in only 4 megabytes. So unit will double the time, cut, load in, load out, just double, almost double, cut. Approximately is double the time of the load in or load out time. And then we also provided some hardware to speed up this process. We have ready queue for the ready to run processes. Okay, we maintain these ones. So that means we keep the process which are ready to run. If some process has been loaded out, of course they need to be deleted from the ready queue. They are not ready to run. Okay, so this is the idea, which have memory images on disk. So on disk, so that means mainly is in the backend store. So that means even it is loaded out, but we temporarily save it down, means still has a chance to be scheduled. So we combine both sets. One set is in the memory, the other one is in the backend store. So we put all of them into the ready queue. Okay, so all of this one in the ready queue, so they are ready to be scheduled. So this is seems a better way, because those processes maybe still need to run to finish, and you need to provide the feedback to those processes as well. Just because you still have direct access to the memory, it seems like memory, but maybe a little bit slower. You have to still need to read those data into the memory before you run, because even you have direct access, but it's a lot of memory, just means you don't need to do like the open a file and so on, like those things. So you can you already know, okay, I loaded something into some spaces. So for this space, starting from is for one process, and this one is for another process. So that means the direct access means that you can load that data quickly into the memory. So that means those processes are still in the ready queue, just ready to be scheduled again. Okay, this is just for the good list of the system. We want to keep those processes moving forward. Okay, rather than just just waste the running, because it is not finished. Maybe already finished 50%, so it still can be scheduled after we finish some high priority processes. Here give you a diagram which is easy to understand. Okay, so we have operating system, we have user space in the memory space. We usually keep the operating system in the lower address, just because in fact we have some interrupt vector table here, so that's why we prefer put the operating system program and code in this lower address as well. The reason is that we can just keep running, we can keep running, access those interrupt vector easily. And then for user space means we save the space for the user processes. So swapping means we want to get something, but before we get something, because this is almost full, there's no space, so we must swap out. So we save some process into a backend store, and then get one from backend store into the memory. Maybe this one was the one which has been swapped out when we run P1. So this is just like exchanging repository, and then you can just based on this exchange repository, we get access to some processes and exchange the space. We traded time for space, just because we don't have that much space to run both processes, to keep both processes into memory. Okay, so always you have this chance, because maybe you have bigger memory, but you may have a bigger program to process. You may also process multiple processes, run multiple processes at the same time. So this is swapping. We have the context switch. So it's similar like we do the CPU scheduling, because this one also involves CPU scheduling, because you will just not only the context switch for the running environment, but also for the memory transfer time. So you will include additional time. If next process is to be run is not in the memory, we need to swap out a process and swap in that target process. So context switch time can then be very high. Here we give one example. For example, the speed for the transfer is 100 megabytes. So it's bytes, not bit. Megabytes. So to hard disk process swapping to hard disk, that means from memory to hard disk. And this is 100 megabytes process. The size of the process is this one, and the transfer rate is 50 megabytes per second. So within this speed, it takes 2 seconds. That means 2000 milliseconds. Okay, and then plus swap of the same size swap in. This is swap out. So it's double. Okay, almost double. So total context switch swapping component time only for the swapping. So this context switch for the swapping component time is already 4 seconds. Okay, already 4 seconds. That will be slow, because you have 100 megabytes and the speed is only 50 megabytes, and then want to do this change. So it takes 4 seconds. We can reduce if we reduce size of the memory swapped. So of course this is only proportional to the size of the data to be swapped in or out. So we can reduce the time if the size of the memory to be swapped is smaller. Okay. So if we know you just swap as needed. You don't need to swap too much. Okay? That means if we know how much memory we needed. And then we mentioned, in fact, we don't need to provide the additional mechanism, but we do provide some APIs for this swapping. So we have this request memory. You want to request how much, and then you finish, you release the memory. Okay, so that this is implemented. That means for this swapping will be done by the operating system, but when you want to do the swapping, you just do like this way: request the memory, release memory. Of course, maybe this one is also only used just implicitly in your program. So that means maybe you will just run programs, run processes, and then multiple processes. You do multi-threaded programming. There's not enough memory for your multiple threads to run at the same time. Maybe you already do this one, but it will call this system calls, but without your knowledge. That means you are not aware of this one as well. So this system calls has been used during the execution of your multi-threaded program. Okay, for some cases. So let's look at the example. Maybe I already ignored the 2 slides for this section. If you are interested, you can take a look, but they're not so important. That's why I don't want to make it too complicated, because swapping, it seems less important content for this chapter. But the concept is important for you to understand. Just introduce this one. Let's look at, for example, for the mobile system, whether we have this implementation. In fact, we don't support this one, because in the mobile system, usually we don't use memory disk. We use only one, use flash memory. Okay, with flash memory. So this flash memory has a problem, because its flash memory is faster, but it cannot do many times read and write, because it have a life cycle, limited time of write cycles. Read is okay, but write has a problem. Okay? And also the space is small, and the poor throughput between flash memory and CPU on mobile platform. So CPU, we have some memory, but mainly we save all of our data in flash memory. Okay, so if you change the data between flash memory and CPU processor memory, that will be registered or something like that. It is still not good enough, because this is still slower, just like the disk. Okay? So instead, if we found our memory, flash memory is not big enough, because this is the main memory you will use to run all your processes. If we found currently we have a heavy load on with respect to the memory usage, so we have to ask some process to stop to run. So iOS, like iOS, we ask apps to voluntarily relinquish. That means withdraw. Okay, just release some allocated memory. So some read-only data throughout. So that's data, for example, you didn't change them, you just read it, and then you throw out. That means no need to save it a copy for this one, because it's already there's a copy there, so you don't need to load it again. So, and then reload it from flash if needed. If later you need it, you just load it from the flash again. Okay. If we cannot free some memory, will result in termination of some apps, because there's no enough memory to run those some new apps. Maybe will terminate some apps. If they don't want to free their memory, then we have to terminate those apps. So you can open it again once maybe you are finished some other tasks. And Android, we just terminate apps if low free memory. Okay, that's even stronger. Okay? But first, write application state to flash for fast restart. So that means like we do a copy of the context, just save it. So later maybe we'll run that application again. So we'll just save the current state of the application. Okay. So both of these iOS and Android will support paging. So paging will be mentioned later. Paging, that means we segment the logic space of program into pages. So we load in, load out based on page. So later we'll have different algorithms for the page-based memory allocation. Okay, this is for the swapping. Okay, for the swapping. Let's just continue with a little bit for the continuous memory allocation. We can finish only the concept part, and then we'll continue the algorithm part next week. So because most of the content we already mentioned before, continuous allocation is the easiest one, correct? So that means you want to allocate continuous memory. Of course, maybe you put several continuous segments, we call it partition, but each partition is continuous. Okay. So main memory must support both operating system and the user processes. So your main memory will run operating system, and the operating system can run your program. So your operating system also saved in the main memory. So that means we need to know where to save the operating system, where to load user processes. So the memory is limited resources, so we must allocate efficiently, correct? And then continuous allocation is one early method. So in the past we used this one, but now of course we have some even more efficient algorithm, because continuous allocation may be waste space as well. And also each time you load a big component, big segment, so whether loading and load out, this one have a large amount of data transfer. So later we use a segment. For example, you have different segments of your programs, data, code, and so on. And then you can use this structure. So just chop the pieces based on logic segmentation. Okay? So that will provide you more flexibility and also have higher utilization degree for the memory, because you don't need to load whole, load partial. And also one part is already a logic unit. So main memory usually we usually put them into two partitions. We just we call it low and high. For the low one, usually we reserve them for the operating system and the interrupt vector. Right? So that's why we want to put the operating system into the low, just because usually we put the interrupt vector for the on the low memory, because that one is already coded into the hardware. For example, related to hardware related interrupt, you must respond quickly. So we have fixed the address for those interrupt. So this we maintain interrupt table, and then each table will maintain the address for which interrupt, which routine to run, and so on. So that's why we just occupy the low for the operating system and the interrupt table vector, and then we put our user processes on the high. So this is later you will find an example. I think maybe this is very general. Like Linux, Windows, they always use this way. Just put the low for the operating system ones, and then high for the user processes. And then just because this is a continuous allocation, each process contained in single continuous section of memory. So here is the most basic case. Later you will find out, okay, so that means maybe it's not only one, but here you just think about, okay, one process, we put them into a continuous segment, continuous section of the memory. Okay, so just put all of the things, move all of the things from the logic to the physical, and keep them continuous as well. So in your physical space, you will map from the logic one, so that will be the same order. So that's easy, because if like this one, we only need to know where to start, what is the range. With these two already enough for us to find the address. So that's why we have two registers. We already mentioned this one. We need to save the base and the limit. That will be the smallest physical address, means the starting position of that section, and the range is for the limit. Okay, so we have these two registers to save the starting and the size. Okay, and then the memory management unit will map the logic address dynamically. Then based on the base and the limit, we already can find the location. So dynamic means you can change the base. Limit you will not change if it's the same type of operating system. But you can shift into other locations by changing the base. So this one will give us good advantages, because for some kernels you already finished the homework 2. Homework 2, there's a programming problem. It's loadable kernels. So for some kernels, if are not used recently, we can load it out. And for some, if we need it, we can load it in. So we only to keep a base and limit for those modules ready to load it in and out. Okay, so this is called a transient. That means it's only temporarily staying in the memory. We use it, then we save this one, we keep them in the memory. If we don't need it, we load it out. And but ready to be loaded in, just prepare two registers for that kernel module, loadable kernel module. Okay, so just based on this one, we can quickly load it into the memory. So for example, like this loadable kernel module, and we already have the limit and the base. Okay, yeah, the base is here. So base and the limit, we have these two, and then we can calculate its physical address. Okay, quickly we can find its address. And with these two, we also can load the data quickly. We already decide where to locate, where to save those data. So hardware will support for this relocation and limit registers. So we'll test whether it is allowed access based on this mechanism. So we already showed this similar example before. So CPU will generate a logic address. It means during compilation, we will generate a logic address based on the how many bytes far from the starting position of the program. And based on this one, you will test whether the limit is exceeded. For example, if the total logic address space is 4 megabytes, but you have address which is 6 megabytes, that is not possible. So with this 6 megabytes, it is already larger than you got this one. Okay, for example, this address space is 2 megabytes, and then you have 1 megabyte address. So this one is less than 2 megabyte, yes, and then continue. And then we have a base, maybe it's 1 megabyte. And then based on this one, the base is here, and then the definition is 1. So 1 plus 1. So you got 2. So this is 1 plus 1. That's how we do this one. Okay? We calculate the address by doing simple calculation, addition. Okay? Addition between the base and the deviation, or the logical address. Okay? Logical address just give you the starting from the 0. So what's the deviation? And then the base will give you the starting position here. Okay? Starting position of the for the process to start in the memory. Okay, let's just stop here, and next week we'll talk about multiple partition allocation and the different algorithms, and it will cause fragmentation issues, and then we'll continue with the segmentation algorithm, paging algorithm, and then conclude this memory management chapter and also our course. I think maybe next week we have a little bit shorter time for our instruction. Okay, that's all for this week, and then we'll see you next week. Thank you. Bye.